Hi there. So today we'll be looking into a new architecture which is there in the market. Earlier, we all are familiar with the transformer. We know before that there was something known as RNN, but now there's some downside we are facing with transformer, which will be a big problem in the future. That's why we started moving to other architectures, which is a merger of previous models like RNN, SSMs, and some other new techniques we are having. So we'll start it with the Mamba. The basic architecture is known as Mamba. The name comes from the ideology behind the name is very funny because what happens is original name of our architecture is selective scan structure state space for sequence model. So there are a lot of s in a name, so that's why they say the when you pronunciate it, it's like more like a s. So it's a sound of a snake. That's why they call it a mava. Moving further to the next slide, it will be so what I'll be introducing here is first I'll go with the state space models. I'll be introducing this the main core behind the Mamba, and then we'll be moving how Mamba use this state space. I have splitted this presentation into three core parts. Firstly, we'll be looking what's the issue we are having with the transformers. I mean, that's why we moved to Mamba. Then, what is basically a state space model, and how the state space model is again involved in Mappa. So this will be flow of today's presentation, and we'll be moving accordingly. Let's start with a problem with a transformer. What happen is happens is like a transformer look into a sentence as a sequence of tokens. So using some tokenization technique, maybe it basic white space division or like other tokenization technique, it splits a sentence into discrete inputs as it's visible here. So it starts taking a token by token into it, and the benefit it gets over the time with that tokenization is at any point of time it can look into past and find a connection with some previous token individually. So this is one of the plus point the transformer have right now. They can look into past and create a bond, a special bond with other words, whatever came into past with the current word. So how things goes is the main workhorse behind this transformer, which do all this processing of merging with the previous words, is done by self-attention, the attention layer itself. So it enables the uncompressed view of a sentence, and which creates this kind of metrics. This is known as attention metrics. So if I go with the example, I can say that uh, in this you can see if I have a two-word name in my, the name is related to my, but if I have a four token sequence, I can see that Martin, my name is Martin. Here Martin is much related to name itself and less to my end, is because these are again helping verbs and pronouns. So it shows how this token is related to its past token, and that's how these words create relation with each other, and that's a plus point that that's a blessing with our transformer right now. So one other thing that transformer do very well is parallelization. So how it does that is if I have to compute this thing, if I say my name. So if I have to compute this thing, I can do it very easily. I don't have to. If I say my and name, I have to compute this attention. And then if I have to compute name and is, this is separate attention in this line. Name and is. I don't have to compute this attention first. I can compute this attention first, also like parallel in parallel fashion, which is done through multi-head attention thing, which boost the training part of this transformer. So this parallelization is speeding up the training with the transformer, but with a blessing, there's always some curse followed behind, and there's one this big flow which a transformer is facing is whenever I have to compute the attention for a sequence of length L, I have to compute that complete L square matrix. And during the inference, I have to calculate again and again for each word. If I say hello, then for exclamation hello, then for my name, my exclamation hello. And this is a time complexity of L square. This is a time complexity of L square, which is creating hindrance in inferencing actually. So this will be problematic in a long run. Like if we have a sequence length of like 1K, and then if we move to 10K and then 100K, this inferencing face a lot of time related issue. Now, this is again a report card of a transformer, like fast in training but slow during inferencing because of its quadratic nature. Are RNN really a solution? Now, because we are done with the transformer, we have to come back to where we started, RNN. So let me introduce what RNN is basically. So recurrent neural network. So what they does is at a timestamp t, they take some input, let's say xt, and they have some previous hidden states. They'll update that hidden state and produce some output yt. If I look into unfolded manner, it will be like if I am standing at timestamp t, I'll take input xt. I'll take a hidden state from t minus 1. With the hidden state of t minus 1 and current input, I'll create a new hidden state and I'll produce a current output. So this is a flow of a recurrent neural network. These are sequential neural network basically. So this is just a loop which is repeating every time this loop. xt, ht minus 1, and then create yt, xt plus 1, ht, and then yt plus 1. So this is what RNN does basically. So if I just read, when generating the output, the RNN only need is considering previous hidden state and the current input. Uh, but again, there's some kind of problem with the RNN also. Like I'll keep it on to audience. Like if I say that in this diagram, I'm having hello exclamation, my name is Martin. Uh, if anyone can guess what's the issue here is, like you can take a try. What's the issue here in this diagram?
Just focusing on the previous step.
So what happens is, like if you see this orange block is missing here now, because it just take a small window where they can just look, and it keeps on looking into previous step, and it over the time forget the earlier things whatever they have saw till now. So RNN tend to forget information over the time since they only capture one previous state. This sequential nature of RNN create another problem, like we can't do parallel training, which we were doing in this transformer, because this is again a sequential nature and we can't break it and do separately and this separately. Over the time, there was solution created for this also, but when RNN was there, this was the issue with the core RNN. Now coming to, again, if we visualize how these two things differ from each other, is like a transformer training is fast, but for RNN training is slow because of no parallelizable ability. But while inferencing, a transformer have to do this L square time complexity, but for RNN it's just a N or L basically, because it's a sequential thing. They don't have to compute again from back. They just take a previous hidden state and they compute over that next, and they move it accordingly. So can somehow we find an architecture that does a parallelizable training like a transformer while still performing inference of this RNN, because we somehow to find a solution which is a kind of middle ground between both of these things. So this issue is kind of resolved over the time. And coming to our second part, it will be SSM, the state space model. But basically, state space is, I mean, everyone have heard this word. I think this state word in Transformer also. There's this state of a vector or something relation to that. But I'll tell what how that exactly comes into picture. Let's imagine there's a XY coordinate and there's a maze here. So state just basically points out what is your current location or what is the location of any point in a space. And the state space is the map of all the possible states or the all the possible location we have. Each point again represent a unique position in a maze. So how I can just tell it or combine it in one line, I can say that state space representation shows where you are currently, where you can go next, and what changes you want to make. So if I'm at a current state this, and my target is I have to go out of the exit. These are the changes I have to make. I have to move further, and I'll go like this. So this state space representation, if I somehow combined with our experience, previous experience, it will be more like a vectors in our spaces we have. This is just a 2D vector I have right now. This vector is again from the maze itself. I mean, like where I was, where my exit is, or what, how far my exit is. If I create a vector for that maze, the embedding for that maze, it will be something like this, like x, my current x position. Huh. So it will be more like my current X position, my Y position, and how far I am from exit right now. I mean, in this graph, if I say that X is 4, Y is 1, and my distance from exit will be something like 7. So state basically just represent where our vector is it in n dimension, whatever the dimension of that embedding is. And if I just say like uh, if I just say it in one line, SSM basically describe how these uh, states are modified so that we can make prediction of whatever what their next state could be depending on some input. So if I say like I'm at a given timestamp t, what SSM want is to take an input of a sequence xt at that time stamp with the help of the hidden state, like latent state or hidden state xt, and we can move to or derive some output that is yt. So how this thing goes is like if I am on this vector in some dimension, using some hidden state, our prior knowledge will change this vector to some this vector. So this is how this state space model works. It's more like making the changes in the embedding space itself. So these are basically state space model. If I just tell it in a lemon language, uh, what this SSM does in our how this SSM help in our context is it will take our input and they'll predict some output. So this is just a basic role. If we start with how SSM will come into picture. If I like, if in case of transformer, it's like a encoder or a decoder which take input, which give output, and this is a transformer. Here it will be SSM. SSM again, I told like it will take help of some latent state, modify the current input, and try to push it toward the predicted output or whatever representation we are looking for. Mm, there's a very prominent use of these two equations in future. If right now, like I mean, these will be just a normal equation, but how this works is like we have a state equation which will help us to predict the new state. We'll simplify this thing. We'll use it as a hidden state. Actually, we'll call it as a hidden state HT. We'll use our previous state input and we'll find some new hidden state, and with the help of that we'll produce some output. I'll tell you how these equations work and how this comes into picture, but this is the introduction to these two equations. These are the core of this complete SSM itself. uh, Again, the state equation and the input equation, these will help to get a input to the output phase. If I visualize this thing, I can say that I have a state ht. uh, there will be these parameters a and b. So at state ht, I'll be having input xt, which will merge with somehow in some change format because it get multiplies with some b. With the help of xt and the previous ht, I'll get new new state basically. So this is one equation, and another is the output equation. Now I have new ht. Here it will be h dash t, but over the time I'll change that. This is new ht, but still it will take help of input itself and it will produce some output yt. So these are the two equations, state equation and the output equation, which will completely justify how this state space model works. So if I visualize it in a flow, it will be more like, I'll start with this. I have a bxt, I'll have x, it will get multiplied with b, it will be here till here. I have aht, I'll take h, I'll multiply a. Now I'm here, I'll join it here and I'll produce the new h again. With the help of new h, I'll multiply with c, I'll come here, and there's x t multiplied with d. If I say we have already, we know this thing, what this connection is. This is a skip connection, just a skip connection, or in transformer language, they say this is a residual connection. So with the help of new updated HT, I have and a C matrix with some inference from DXT at a point of time wherever it required, I get my output YT. If I start with how this flow works, in terms of metrics, it will be like this. I have input multiply with the B, I'll get this matrix. I'll start from here. I have a previous hidden state. I'll multiply with A, I'll get this matrix. I'll sum these both. I'll get a new matrix. This is a new matrix. I'll multiply with C, I'll get some another vector. And with summing up with this vector, I'll get my output. Leaving that thing behind for a moment, this complete architecture, this gray shaded area is known as state space model, because what it does is it take a state, this state representation that is a hidden state in a given space of inputs, and produce a new output, which is another representation. So this is how this state space model works. In terms of equation, for now we'll ignore this skip connection because that's not a hardcore part of this equation. The required part is just a ht, which is produced with this equation, and then using this ht, I'll produce y. So this is the thing with state space model. Coming to this part, what happens is right now this is a time-based thing. This is xt yt at a given timestamp. Uh, this is continuous time representation, and as we have seen before, word, if I have a sequence, it is discretized into a tokens. But this thing is not here right now. This is just a time dependent, and we can't calculate anything on basis of time. We have to chunk it into something. Like for image, it is pixel, and for this sentence, it is word. So now it's time for discretizing this continuous equation. How it will work is like I'll uh, do use this zero fold technique. What it does is, like, if I have a timestamp 1 2 3 4, I'll hold these words for these timestamp. If a sequence has like n tokens, it depends on me what step size I'll take, whether I'll tokenize it in each one token at a time, or I'll divide it into multiple token at a time. For this, I use this delta parameter for discretization. In simple language, if we start saying it's nothing but tokenization, they'll just tokenize the thing. And now they'll start working on these tokens. So if I introduce what step size is, it tells how long we have to hold the value by a new learnable parameter with the help of step size s. It represents resolution of the input. If I give an example in term of image, if I have a smaller resolution, I'll be having pixelated image. But as soon as we improve our resolution, the image will be more clear. So if I have a step size which have a lesser resolution, my meanings will be not that defined. I mean, not directly here. If I have a step size which has a bad resolution, if I say, it will be big chunked sequence. So at that time, my meanings will be not that clear, or the context will not that clear. But as soon as we improve our resolution quality, the chunking will be in terms of individual token, and at that time, the discretization we have done will create a good context for our inferencing part or training part. So how this thing works is again using this zero fold technique. This itself is another paper. So I'm just using the name itself to tell. You can refer to this technique for getting more detail. With the help of discrete input, I'll get a discrete output also. I mean, that's what we are doing. And these are the two equations which we use with the help of delta to produce a discrete like A bar and B bar. So now these are the new words we'll be using in our equation, because now our equation is discretized. It will be like this thing. Now from continuous, we have moved to discrete SSM. Now the equation is also changed. Earlier it was HT and HT. Now we are not having a function in term of time. It's a sequence to sequence thing. So if I say here it was in terms of time at time this, time this, time this, now it's in term of k. If a sequence is of length L, I'll say at a kth location or k minus one location, I'll move like that. So if I say I'm at this location, this particular location k, if uh, I want to predict a word for this location, how I'll go is I'll take a matrix A, I'll take a hidden state of previous location, I'll do calculation and predict new hidden state for this location K, and with help of that HK, I'll predict YK, the new YK I'll be getting. So now this discretized equation will be coming into picture. Uh, how this like resemble with RNN will be something like I'll talk into future, but I'll just tell how whatever I've told like verbally how things work is like if I'm at H0, I'll be having no hidden states before me because there's no AH minus one. I have to start right now. I'll be having just a B matrix and X0 input at that time. I'll be producing Y0 with the help of this H0. But as soon as I move on next time step at not time step, I mean k plus one something. If I say k1, it will be like previous hidden state that I have just calculated right now. It will be used here. With help of that, I'll be getting new hidden state, and accordingly, I'll getting the new predictions. So this will goes like this. Uh, this representation seems a bit familiar because we have seen similar thing in RNN also, where over the time that hidden states get improved. We are calculating new hidden states. So this was the thing in RNN. Hidden state was getting improved, and in case of SSM, the similar thing is happening. If I unfold this image, it will be like this actually. So this is SSM, this is RNN. Here, hidden states were getting changed over the time with a t time step. In case of SSM, it's discretized now. It's in terms of k minus one. So again, we use the ideology of RNN itself and created a model named as SSM, which use the concepts of RNN itself. Even though we never directly called it RNN, but it's a recurrent model itself, which is just SSM. They are calling it as a SSM. How they are using convolutional representation, this is also a good uh, ideology they have started using with these SSM now. So what happens is there's a kernel in this convolutional networks. What is does is if I have an input, if I have an image of this size, and if I want to apply some filter, let's say filter to that image. If my filter is 3 by 3, my output will be for sure smaller output in this image. It's represented like this. We can use similar kind of technique in text also. We can create some kind of filter. With the help of these three words, it will produce some new output. We can use filters like this in text. Uh, this is the numerical representation of that thing, but I'll come back to this representation in next slide. How this works visually, if I just represented it. Uh, for an example, we just have a padding here. Usually, there is no padding before. There will be some starting symbols like CLS or next word, next sequence, something like that. It will move like this. It will take a kernel over to these three token. It will produce some output. It will take to these three words. It will produce some output, and this is how this kernel will go over the time. Similarly, I think in case of convolutional also this thing happens. Like this filter will move over the time to this, and that's how this new output is produced. And similarly, this is done in case of text also. I have expanded this equation further in my words. So how this thing works is we have seen that h0 y0, then we moves to h1 y1, then to h2 y2. At a current h0, I'll be having bx0, and at I'll be getting y0 at ch0. If I just put this h0 again here, it will be bx0. Similarly, in case of h1 a h0 plus bx1, and I have inserted this h0 from there is now here. In terms of y1, it will be ch1, and I'll put this h1 completely here again. Similarly, I'll be getting h2 and y2. Now, if we see a common trend, what is happening here is if at a yk, here it's 2, the k is 2 here. At a yk, what is happening is c a k b x0, c a k minus 1 b x1. It will go till c a minus a k minus c a0 b xk. If it's a just a three-word equation right now, but if I generalize, it will goes like this. You can just relate a relation from this equation, from these three words. That's how this thing goes. This will be k and 0. This will be k minus 1, 1. And over the time, it will be just 1, k minus 1, and then 0. And this will be k. We can define this as our kernel now. Whatever we were saying previously, the filter or the kernel, whatever we were saying, is now kernel here. So how we can generalize this yk now? If I say my kernel is k, which is uh, related to the length of a sequence, uh, it will be having cab, cab, c a k minus b, and c a k b. CB, CAB, and it will go to CL minus 1B. It will goes like this. And instead of that, I can just write K. It will be KK X0, KK minus 1 X1, and it will go like K1 XK. It will go like this. And now I have Y, KX. If I go back to previous slide, it was YKX. Okay. So this is the kernel they are using to get all these things. This I use this three-word equation only again in. in the image. That's how I get y1. This is CA2BX0, and here till here the K is 0, and this XK comes into picture. So I hope this equation is clear, because this was the one of the important equation.
Yeah, got it, Ankit. And the implication is that uh, like once you pre-compute the entire kernel, this can be done before, and you just apply it once, and with the order of one complexity, you get the entire output, right? Like there is no
Yeah,
need to do
basically,
it.
so they predefined the size of kernel. Right now, if I say this is for the L length, but what actually happens is, if I say my size of kernel will be 4, like in this image, it was of size 3. This was a kernel of size 3 actually. So over the time, it will go over the window of 3 words and computer next Y0. So
Hmm.
I'll come to this thing, because there is again an issue with this kernel also. So what happens is, right now I have these three representation, a continuous time representation, which I have discretized, uh, with the help of which I get a recurrent network we have saw earlier, which is efficient in inferencing. With the help of convolutional, I get parallelizable training, because we are moving over the many words, and I can do it without the need of a same previous word. I can do it in another line. They don't need to be together itself actually. So if I look into terms of image, I can use multiple kernel at a time. Until unless they are not overlapping, I can use them. One kernel can be in this corner and one can be in this corner. So this create a parallelizable effect. And if we remind, this effect was there in transformer also again. Issue with this thing is, this is not unbounded. I mean, this is bounded with the context. I can't go beyond the size of this three. I mean, kernels are not dynamic, they are static. They have to be defined earlier. So again, we have to figure out how to use these things. So what the idea was, we can do training with the help of convolutional network, because they are parallel, they are parallelizable, and we can do inferencing with the help of RNN, because the time complexity is L here. These are sequential. So this is the ideology they went with in this model, and they create this model is usually referred as linear state space layer. Uh, Coming to next part, everywhere we have seen this A matrix is there. This A matrix itself decides what should be the next state. It takes the previous state, we multiply with A, we'll get a next state. So the most important thing right now is A matrix, and we have to look how this thing works. So what A matrix does it? It simply captures the information from the previous state and builds a new state. It's a main building block of this, um, what we say, RNN or SSM we have. Uh, this is the formulation version of this A matrix. Uh, A matrix itself defines whether, we want to remember only the few previous token, or we have to capture everything we have seen so far. So again, it only decides how things should be going. But the issue is, so how can we create a matrix which retain a larger memory? I mean, over the time we have seen earlier that there was a issue that my was missing from that block over the time. This thing was happening. I mean, it's a good thing that it is capturing this previous uh, context, whatever it is saying, but we have to improve the size also. Otherwise, our inferencing will be damaged. So what they use is, they use something known as hungry hippo. This is completely another research. Uh, I haven't dived deep into this. This is the just a methodology. I'm just telling that they use this hippo to, I mean, over the time degrade the earlier step. into a concise way without hurting the knowledge of a at a current timestamp. So they use something like this, and the formula is something like this. I mean, I haven't went to this paper. I'm just telling this is the methodology they are using for capturing the previous context with this thing. Now, if we move forward, like what we have right now is we have a continuous state space which is discretized, and we have this hippo. Now we can efficiently handle long sequence because we have somehow figured how to capture the sequence in a concise way with the help of hippo. We have discretized the things, and we started using this SSM. So what we call it is a structured state space for sequences, and this is known as a S4 model. This S4 model is generally referred as a SSM in the layman terms. They don't call it S4, they call it SSM. So this was the SSM that was in existence till now. So how Mamba used this SSM is what we are going to study now. A selective SSM, basically the S4 model itself. The This is the something else, but the SSM was the S4 model. So if I just speak, what is the problem that Mamba want to solve? Like everything is fine now. We have parallelizable techniques also. We are able to look into big context also. But still, there's one issue we are missing is like it doesn't has the ability to focus on some particular word that the self attention was having. I mean, for self attention, it was easy to go back into the past and look, create a relation or the particular attention with some individual word, whatever it want. But it's missing in this Mamba. So two things which Mamba need to fix is one is selective coping. See, if I have a sentence this big, cat love playing with a yarn. The only major thing I require is the subject, the cat, and the object yarn. So this is known as a selective copying in terms of like what we'll be working with. But there's a issue with current SSM is it is linear time invariant. Right now, I haven't said that A, B, C are learnable parameters because those are static parameter and they don't change. If those are static parameter, they don't know how to create a relation with this. Even though with the help of hidden state, we somehow know what is in the previous, but they don't know how to change over the time for the current input or how to create a strong relationship with the previous input. So this is not there in SSM right now because of this linear time invariance problem they are facing with. Second thing they are not having is we all know there's something known as uh, what we have a basic transformer model, and then we have some layers on top of that, like sequence to sequence partial LM is there, then we can change the front layer to question answering layer, but this thing is missing in SSM. What happens if it is I do zero shot or one shot prompting? If I ask what is 1 plus 1, answer is 2. Now if I give a prompt what is 2 plus 2, answer should be 4. But they don't have this learnable parameters which goes over the time A, B, and C. This just fails this complete uh, this concept at all. Like they don't know how to understand what is having in previous time because of lack of this dynamic nature of these parameters. If I visualize it, it's more like a B is same in both the scenarios, even though input is different.
Ankit,
Hmm.
okay, so ABC, if they're not learnable, how are we selecting them? Increasing them?
You are not audible actually.
Uh, can you give me one? Hello?
Hello?
Am I audible now?
Yeah, yeah.
Okay, so if ABC are not learnable, how are you selecting them? Like, uh, there should be some method that they are parameterizing.
So I think I have a slide on that if I just move forward to this. Mm. So till now, this was the input and this is the output we have. Input is just a dimension of or embedding we have the sequence, and this is the batch. This is how input goes usually. What is the dimension of these metrics A, B, and C is just a dimension of a vector and the hidden state size. This is currently present in S4 model. Just to and with the help of these metrics, these are static metrics. These are not dynamic metrics. We are just multiplying this B with XT, A with previous HT, and I'm getting some new HT with the help of summation of this BXT and AHT. I'll get something new. But this B should change now over the time if XT is changing. So for that, they have included one another parameter that is L, the sequence length. Now they have this thing, they know what is the sequence length and how things will change over the time. This delta we have seen is the step size. What it does is, like, if a step size is smaller, what it will do is it will ignore the current input word and increase the context of the previous hidden state. I think I don't have a diagram right now. Here it was like if a delta is smaller in size, this effect of this xt will be less and effect of this ht will be more. But if delta is larger, what will do it? It will change the A, which will help in degrading the this effect of this ht now, and it will improve the effect of this bxt. So that's how delta comes into picture. I'll show the original diagram which was given in.
So just to be clear, delta basically give importance either to the input or to the previous
Or
state.
to the
So
hidden
we can
state.
control it to the hidden state. So we can control
Huh,
whether the input should be given more importance or the hidden state, the information stored in the hidden state.
yeah, basically the previous knowledge should be given more importance, so the current knowledge
Uh,
which we are getting is given more importance. So this is
right, right.
the thing they have introduced now. This was not there earlier actually. This is the new parameter they are introducing along with the sequence length. So the static nature is now changed, and now the A, B, and C, this B and C can also take change over the time instead of just focusing on one thing. Because if one shot prompting happens, because of their static nature, they will never remember what happened in past, and the weights will be same because of their static nature. But if these are dynamic, over the time they can understand what changes are happening, and if xt changes, this also need to be changed. Even though previous knowledge is captured, but they are not directly reflected in xt actually. That was the issue.
So when you
So
say B has to be dynamic and you have added a new dimension of sequence length, so this
hmm,
becomes a three-dimensional tensor now, right?
yeah,
And
this
is it learnable now or it's not?
no, this is learnable now. These are dynamic.
Okay.
But again, this creates some issue is like we need fixed kernel. We can't go with the dynamic kernel. And now parameters are changed. So we can't use this recurrent representation, and we lose this parallelizable ability we have right now because the kernels were supposed to be fixed size over the time. In this kernel, we were having these parameters C and A were there, B was also there. Now they are dynamic, which will create some issues. So earlier, when they were static, B and C were static, C will be somewhere here. It was just a sequential scan. But to over the time, if we move to dynamic or trainable nature of these parameters, we have to move to something different. This is known as parallel scan actually. What the idea follows is like it assumes that in whatever order we do operation doesn't matter. until we use associated property. Uh, and with the use of that, they are doing this. I'll show in next easy image. This is just a visualization how this H0, H1, H2 goes over the time. I'll go to next image and I'll come back here. If you look into this image, this is the associative property. But I was talking like even I have to compute A, B, C multiplication. Whether I do A multiply B into C or A, B multiply C, answer is going to remain same. So if I have to add all these things together, I can create multiple threads. The idea of what they have given in parallel scan, actually this is very old concept, so I don't have much of this knowledge, but the idea they are saying is we can sum up these two things together at a time. We can sum up these two things together, then we can sum these three things together at a time, and then we can get a final sum. So this is how these parallel scan actually works. This also helps in one another thing is like when we were doing sequential scan one after another, that previous hidden state current input gives a new output. Then again, this was a for loop kind of thing. I told you this is just a for loop. It was sequential in nature and time complexity was n there. But if I create a T thread, I can do this thing parallelly actually. I don't have to wait for this thing summation of 9 plus 6. I can directly go to 8 plus 7 summation here. This even decrease the time complexity to n divided by t. So this is the parallel scan. If I come back to this image, the same thing is happening here. They are using H0. They are computing this at a time. They are computing the BXT, BX3 for this at a time. Then somehow they are like using this hidden state to create a sweep up for this one at a time. And over the time, this parallel threading helps them to save some time instead of going sequential in nature. Uh, I'm not 100% sure again how this is happening in terms of this scan actually, because this is bit complicated. In terms of this one, I think this is bit clear actually to understand, because this is just a basic calculation. So that's why I use this image for interpretation. In their paper, they just have said a single line, we use parallel scan, and this result into selective scan algorithm. They are naming it like that. So if I get a better resource, I'll share with you. But right now, this is the only option I have with that image. So together, the dynamic matrix B and C and the parallel scan algorithm create this selective scan algorithm. So now onward, we can say that this is a selective scan algorithm. There's another algorithm they are using is, if we remember, there was some paper earlier which was known as flash attention. They were flash attention. This thing was there. They were doing something with hardware. They are also doing the same thing. What they are doing is usually what happens is what DRAM is. If I say that it's a bigger memory with slower speed, and SRAM is a quicker memory. If I say that DRAM is L3 cache and SRAM is L1 cache, this is expensive actually. Like computation in this SRAM is expensive because of a smaller space. You can't do all the computation there only. So over the time, what they are doing, they are calculating in SRAM, bringing back to DRAM, calculating XRAM. This front back was happening, and it was creating a hindrance and decreasing the speed of computation. What they have done is they have fused these calculation into SRAM itself, and they are calling it as a kernel fusion. In our flow, if we look, it is done here in a hidden state actually. Uh, I have a better image of this thing. If I go, this is the kernel fusion actually. These all the green ones are DRAM, which is a slower computation. This fast computation, the kernel fusion is happening in this area. So what actually happens in one kernel fusion is The discretization step happens from continuation. Second thing happen is this selective scan algorithm where parallel computation is happening in O(n/t) time. And the third thing is it multiplies back to CT and produce output. There's another name for this area. They call it as a memory bus because this is the only thing which captures all the memory. The hidden state captures all the memory of the previous thing. That's why they call this area as a memory bus also. And because this is very crucial part, they keep it as an SRAM, the fast memory, and the kernel fusion works in this area only. These are the learnable parameters which are chunky parameters, so they keep them in this DRAM itself because they are not changing at that pace. This HP is changing actually. So this complete model is known as now S6 model. So earlier I was having S4 model, which was named as structured state space for sequence. Now I have joined two more word, which is selective scan. So S4 plus selective scan is now known as S6 model. So this model is the complete model which Mamba uses, and this is the picture that was given in paper itself. I mean, they haven't given these pictures. This is from somewhere else because they just gave this picture and told that this thing is happening, and they just moved on with this picture itself. Coming to how it will look into working perspective is just like a decoder or encoder model we are having where input embedding are there. They go into this decoder block where self attention will be there, layer norm will be there, again some neural networks will be there, and we'll get some output in the end. So again this Mamba block goes like that. If I zoom in, it will look something like this. Inputs are there, they are projected into the bigger frame. This is the skip connection we are having. Then this convolutional is calculated. We have seen before. Uh, there's a bit of confusion with me also. What they are doing finally, they are using this convolutional for pre-training or not. But this selective SSM or the S6 model is there. This is for sure they are using actually. So this SSM model they are using, and again they are projecting back as an output. Uh, Again, if I say if it starts with just a linear projection and expands the input embeddings here, uh, then a convolutional before SSM is applied to prevent independent token calculation to do the parallelizable stuff basically instead of going line by line. The SSM is as per follows. The recurrent SSM is created through discretization. If hungry hippo is applied to improve that long-term dependency. Selective scan is done to again overcome this issue which we lost in this dynamic nature of these metrics, the parallelizable ability. And then there's this hardware algorithm also where we just use that memory bus wala thing. And then we again come back to a normal form with the help of some normalization and softmax, we get our output. So this is what complete Mamba working is. With the help of S6 and convolution, the Mamba works. So coming back to our time card, now what we have is now our Mamba is parallelizable also with the help of convolutional and parallel scan or selective scan algorithm. It's fast also again because of parallel scan is also one of the reason because it decrease the time complexity to n/t. And now we have unbounded context also because of that hungry hippo. It give a long dependency. So these were the missing features which was there in transformer and RNN, and then the Mamba filled that gaps completely. So this was the presentation I had.
Yeah, thanks a lot, Ankit. Really, really helpful and a much detailed presentation, I would say. So we have a couple of questions. Maybe we can ask them. So I have a query around what does it mean? Like you said that we are coming from the continuous space to the discrete space. and now you have different modalities as well, right? Like you have images. So what does it mean when we are working in the text domain? How does that typically happen? Because with transformers, we convert these text to tokens, and then tokens are ultimately converted to some sort of embedding, and that is
Mhm.
given to different layers within the transformer architecture. Can you
Mhm.
go in detail about what happens in Mamba? I think you showed an example, but can you dive into that particular aspect a bit more?
I'll move to previous slide. So I think you are asking how this convolutional is coming into picture in comparison to transformer, what they are doing.
So for example, you take a text key, my name is Abhishek, or something like that.
Mhm.
I think we will apply some kind of tokenization on top of that particular text,
Mhm.
and then we will ultimately expose it to our Mamba, right?
Mhm.
Do we have an embedding layer in Mamba, which basically convert this token into some sort of embedding and then ultimately exposes? How does that happen? Like, what does discretization mean when it comes to text for this
Uh,
architecture?
till now, what I have understood is like the basic RNNs. What was happening there is they were working on the concept of like at each time step how things are working. Like if I go back, uh, so what was happening is like we were just having a continuous flow over the time, but I think it is written here like
So
hmm,
I'll tell you what I have understood, especially because again, because state space models are coming from the continuous domain.
yeah.
Uh, so for signals which are continuous, say for example audio, we definitely have to go through this particular step of discretizing the audio signals, chunking it out, and then ultimately showing it to the model. But I think text itself is uh, discretized in terms of when we create tokens out of it, right? Because tokens are in the discrete space; they are not in the continuous space.
But this concept is particularly just for I think uh, I was just going through the what RNNs actually are. Now, how these RNNs are used in terms of textual, we have
Mm-hmm.
to create a barrier where this timestamps goes away and we start working with the tokens itself. So
Right,
this
right, right.
discretization step was the transaction from the traditional RNN to coming into picture with
Mm-hmm.
the tokens, this sequencing, the textual things we are working.
Makes
So
sense.
to do that thing, they have to use this zero volt technique actually. Like
Mm-hmm.
again, how big resolution you want in terms of splitting of a tokens itself. So this was the
Mm-hmm.
one of the aspect they were having.
Mm-hmm.
Again, it was not that clearly explained in the picture, but with the help of previous different experiments what people are doing in different sources I went through. They just normally call it as a tokenization technique they are going with because they have to discretize this formula also, the continuous SSM formula they were using traditionally in traditional RNNs or SSM in terms of the sequence now, because we can't just go with a timestamp. We have to somehow move to tokens at a kth location or something. So this was the transition there. Uh,
Yeah, no, that makes sense actually. I think that tokenization itself is like the step for discretizing the text. So then we don't
huh,
have to do anything on top of it. It's just about
um,
giving these matrices and then, uh, yeah.
there is another thing also, like again, this SSM was never initially designed for text itself. These were either for some kind of graphical representation, like in terms of audio frequencies or something like that. So somehow they have to come with some solution to use it for text, actually.
Yeah, yeah, yeah.
Mhm.
And also in terms of performance, because we have also seen that SSMs are pretty good, or especially the Mamba architecture is pretty good for long sequences, as compared to, obviously they are way more efficient as compared to transformer attention mechanism. But can you have you also gone through some of the results of why that is the case, or where does Mamba perform better in terms of performance as compared to
So
transformers?
I haven't gone to working site, but the major reason again comes like somehow they'll do this parallel training or some another training, but when coming to real life use, this inferencing is the audience which they are going to use. They'll not train the model; they'll just inference the model. They pass the sequence. Nowadays, if I pass a complete PDF, the issue that transformer was facing is that it has to compute the attention for complete PDF itself, which was again a quadratic time representation. In terms of RNN or SSM or Mamba, they don't have to compute this complete matrix itself again to create a relation. Mamba solve it by selecting a word uh, with this selective copying technique I have told, where they just do this thing, focus on one important thing, one important word, and they just do it like this instead of creating some attention mechanism.
Hmm, hmm. Got it, got it, got it. Okay. I think brilliant session, Ankit. Thanks a lot. And maybe what we can do is, I think the next evolution to this would be because there is this paper called Jamba as well, where they are merging the Mamba with the transformer architecture itself to bring in the performance aspect of transformers. Because again, attention is pretty amazing at looking at attending to the past and then giving context-based information. And obviously, Mamba is way more efficient when it comes to doing the computation bit. So Jamba actually merges both these things. Maybe we can take that up, go through that paper as well, because that will complete the entire loop of everybody knows about transformers. So Mamba merging with transformer, what does Jamba actually does would be quite interesting to actually see.
Actually, paper was again full of mathematical formulas and equations. So the
Right, right,
best
right.
is I use this graphical representation. The best I
No,
could have done.
it was quite good and quite simplified as well. Like it was understood end to end why, what was the problem, and how is the technique actually solving that particular problem. So that was quite nice. Yeah.
In terms of transformer, it's not that much complicated because they are not using anything from previous era.
Right.
They are just
Right.
creating their everything on there. There is this query key metric, and then they are
Right.
computing this self attention with just one formula they have.
Right.
Here they
Right.
are
Right.
sometime they are using RNN, then another things are also being used. This is
Right.
just a
Right.
raw Mamba paper they have presented. This is just a vanilla flavor, and itself they have used I think five different techniques. So
Exactly.
that was
I think it's yeah, it was also like a combination. So Mamba itself is not just one paper. I think it's a
Mhm.
series of papers that have come for the past, I don't know, 20, 30 years maybe. And then those techniques combined that formed Mamba. So yeah, it was quite complex for sure. Yeah.
Even though when Mamba first applied their paper to some conference, they got rejected because they
Rejected.
thought
Yeah.
this is just a overhyped thing they are
Yeah.
doing
Yeah.
now.
Yeah. 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 Yeah.
But after they got some results, I think they are their most targeted part was toward the inferencing side, where like over
Mhm.
the time people will be facing some issue. I mean, in
Mhm.
transformer also they are now improving over the time, but
Mhm.
Mama did it in different way instead of
Mhm.
using
Mhm.
transformer. They used the superpower that RNN had earlier
Yeah.
and time complexity.
Yeah. Yeah.
So I think that was the only positive side of this paper using RNN instead of transformer.
Mhm.
Uh,
Quite brilliant, yeah.
Thanks for
Thanks a
sharing.
lot, Ankit. Yeah, thanks a lot, Ankit. Hope to see you soon on these sessions. Yeah.
Thanks, Ankit. Thanks.
Okay, bye.